Welcome to the deep dive. So, today we're opening a file that, well, it reads less like a standard engineering report and more like a locked room mystery.
It really does. It's a classic troubleshooting thriller. We're looking at documents about an LNG carrier that's a liquefied natural gas vessel that had just come out of dry dock.
And for anyone who doesn't follow the maritime industry, dry dock is supposed to be the big reset button, right?
Exactly. It's the major service. You inspect everything, you fix everything. When a ship leaves dry dock, you expect it to be in absolute peak condition.
It's like a spa day for a multi-million-dollar vessel.
Yeah, you expect things to run better, quieter, more efficiently.
But that is not what happened on this ship. Almost immediately after they left, the crew saw this. Well, this terrifying trend in their nitrogen system. Before the dry dock, their compressors were running, 9 to 12 hours a day?
A very healthy rhythm.
Yeah.
Plenty of downtime, plenty of buffer for maintenance or, unexpected issues.
Right. But post-dry dock, those same compressors spiked. They were running 19, sometimes 22 hours a day.
Just running nonstop.
Basically, yeah. And that is an immediate, massive red flag.
Oh, absolutely. When you see machinery running that hard, 22 hours out of a 24-hour cycle, it's not just busy. The system is under extreme duress. You've got almost zero margin for error.
So that's our mission today. We're going to figure out why. Why would a ship's nitrogen demand practically double overnight right after a service that was meant to fix things? Is it a huge leak? Is the machine itself broken?
Or is it something much, much smaller? It's a fantastic case because it really shows you how these massive vessels can hinge on tolerances measured in, tiny fractions of a millimeter.
Okay, so let's start where the crew started, with the numbers. When you have a supply and demand problem like this, you have to check both sides. So did they look at production first?
They did. It's the logical first step. I mean, if the compressors are running 22 hours, maybe they're just not making nitrogen efficiently anymore.
Maybe the generators are failing.
Exactly. But the data ruled that out almost immediately. We've got the logs here. Generator number 1 was pumping out about 85 to 95 cubic meters per hour.
And generator 2 was doing about 65 to 75.
And crucially, those numbers are almost identical to the pre-dry dock figures. The generators were doing their job.
So supply is steady. The ship can make the nitrogen just fine.
Which tells you, definitively, the problem is on the demand side.
The ship is just eating it too fast.
Exactly. It's a consumption issue. So the engineers, they start the hunt. They call it rounding up the usual suspects. You start walking the lines, looking for leaks where all that gas is being used.
And on a ship this size, that's a huge job. You're checking flanges, pipelines, valves. The docs say they check the barrier spaces first.
Right, the IBS and IS, the spaces around the cargo tanks. A leak there is a huge problem. But consumption there was steady. It was normal.
Okay, so a small sigh of relief there. But then they looked at the seal and purge header.
And that showed a marked increase.
And the engine room consumption.
Another spike. So they've narrowed it down. They know the gas is disappearing somewhere in the machinery spaces.
Yeah.
But here's the frustrating part.
They couldn't see anything.
Nothing. They walked the lines. They checked all the piping. No hissing, no damaged pipes, no loose flanges. The culprit was completely invisible.
So you can't find it with a flashlight. You have to switch tactics.
You have to trap it with logic. They moved to an isolation strategy.
I love this part. It's pure deduction. They start shutting off the nitrogen supply to specific machines one by one to see when the consumption dropped.
Exactly. They started with the fuel gas purge valves. They even cracked open the outlet flange to physically check if gas was passing through when it shouldn't be.
Nothing.
Bone dry. Then they isolated the high-duty compressors. Again, no change.
And then they got to the low-duty compressor, LD1 specifically.
That was it. That was the breakthrough. They isolated the seal gas line going to the LD1 compressor, and on the flow gauges, the little float just shot straight to the top.
Maxed out.
Maxed out. No fluttering, just whoosh. They'd found the smoking gun.
Okay, so they know where it is, the LD1 compressor. But this is where the story gets really, really interesting for me. Because finding the leak is one thing, but understanding why it's leaking. This wasn't just a busted pipe.
No, this was deep inside the compressor itself. We're diving into what I call the carbon ring paradox.
Okay, break this down for us, because carbon ring sounds simple, but the mechanics here are, well, they're pretty counterintuitive. We're talking about the compressor shaft seals, right?
Correct. So, to keep high-pressure gas from escaping around the spinning shaft, they use these special seals made of carbon rings. Now, these aren't like a rubber O-ring on your garden hose.
Right.
They're segmented. They're usually cut into 3 pieces, like a little puzzle, and they're held together by a spring on their outer diameter.
Okay, I can picture that. 3 little arcs of carbon held tight by a spring around the shaft. Now, my logic says if you want a good seal, you want that to be as tight as possible.
Intuitively, yes. You would think tighter is better, but this is where mechanics get really tricky. The manufacturer, Cryostar, explained this in the documents. It turns out you can have a situation where the carbon ring is actually too tight.
Wait, how does being too tight cause a leak?
Yeah.
That feels like it defies physics.
It's what we call a tolerance trap. Imagine the carbon ring's internal diameter is at the absolute low end of what's allowed, so it's as small as it can be.
Okay.
And then imagine the shaft sleeve it's sitting on is at the high end of its tolerance, so it's as big as it can be.
So you've got a really tight squeeze.
Way too tight. And remember, the ring is in 3 pieces. If the inside of that ring is too small for the shaft it's trying to wrap around, the segments can't butt up against each other properly. The shaft itself forces them to push apart.
I see. It's like trying to put on a belt that's 1 notch too small. The ends just won't meet flush.
That's a perfect analogy. You create these tiny little gaps between the segments because the ring physically cannot close all the way around the shaft.
So because it's too tight to hug the shaft, it breaks open at its own seams.
Precisely. And in the world of high-pressure gas, a tiny gap is a superhighway for that gas to escape.
And they had the forensic evidence. The crew checked the pressure readings. The technical manual says the first stage seal pressure should be around 25 kilopascals.
Yeah, 25 kPa, that's normal.
On this ship, it was reading 47 kPa. The bulkhead seal was at 50. The pressure was nearly double what it should have been.
So now the crew's probably thinking, great, this part is defective, we've got to rip it out, replace it.
But they didn't. And this is the wildest part of the whole deep dive for me. The manufacturer's advice wasn't replace it. It was just let it run.
The run-in solution. It's a very old-school concept for a very high-tech machine. Sometimes these brand-new carbon rings just need time to wear down.
That sounds insane. Hey, it's leaking dangerous amounts of gas. Just keep using it.
Well, in this very specific case, yes. The idea is if the ring is too tight, running the compressor creates friction. That friction gently, very gently, sands down the carbon material against the shaft.
And as it wears away,
the internal diameter gets just a tiny bit larger, the tension releases, and the segments can finally snap together and sit flush.
closing the gaps.
Closing the gaps. The machine literally has to wear itself in to work properly.
That is just a fascinating paradox, but I want to pause for a second. We said the crew ruled out production issues right away. But looking at the docks, there are so many ways production could have gone wrong. It's worth touching on those false flags.
It is, yeah. Because high running hours often do look like a leak when really the generator is just becoming inefficient.
Like the heater, for example. Why is a heater so critical for making nitrogen?
The nitrogen generators use membranes to separate nitrogen out of the air. And those membranes are, let's just say they're very picky. They need the feed air to be at about 50 degrees Celsius.
And if it's not?
If the heater fails or the regulation is off, the capacity of the whole system just drops like a stone.
So the compressor has to work way harder to make the same amount of gas?
Exactly. Then you've got filters. If a feed air filter gets clogged, you get a high differential pressure across it. It's like trying to breathe through a pinched straw.
Yeah.
The system is choking.
And the really scary one on this list? Oil carryover.
The membrane killer.
Mm-hmm.
That's the nightmare scenario. If the compressor passes even a tiny bit of oil mist into the system, it chemically destroys the membranes. And that's a catastrophic failure. You're not just fixing a seal, you're replacing the heart of the entire system.
But in our mystery, they knew the heart was healthy. It was just bleeding out from one of the extremities. Which brings us to the so what question. Why panic about this? Okay, the compressor runs 22 hours. So what?
Oh, it's a huge deal. And the sources are very clear why. Nitrogen on these ships isn't just some utility gas. It's a critical safety system.
It starts with preservation, right? The cargo tanks.
Right. When the ship isn't carrying cargo, you can't just leave those tanks full of normal air. It has moisture, it has oxygen.
So you have to fill them with dry nitrogen. And we're talking about an oxygen content below 3% and a dew point of minus 45 degrees Celsius.
Incredibly dry. It has to be, to prevent corrosion and protect the insulation. But the bigger issue, the reason the 22-hour runtime is so terrifying, is the safety margin.
There's a rule in one of the reports. N2 consumption is to remain less than 50% of supply capacity.
That is the golden rule. Think about it. If you're running at 22 hours a day, you're using almost 92% of your capacity just to keep things normal.
You have no bandwidth left.
You've nothing left to give. If a real emergency leak starts somewhere else, you can't compensate. The system is already maxed out.
Let's quickly define those barriers. We see the acronyms IBS and IS all the time.
Right, IBS is the interbarrier space, and IS is the insulation space. Think of an LNG tank like a high-tech thermos. It has layers to keep the super cold liquid contained. Those spaces are the layers, and we pressurize them with nitrogen.
And that seal gas we were talking about, the one that was leaking, it's also a barrier, right?
It is. It's a two-way shield. It blocks cold gas from freezing the compressor's gearbox, and it stops lube oil mist from the gearbox from contaminating the whole system.
If that fails, it's a very bad day at the office.
A very bad, very expensive day.
So we've solved the mystery. We know why it's dangerous. What's the final piece? Vigilance? How do you catch this before it gets to 22 hours?
It really comes down to discipline testing and record keeping. The daily logs are your first line of defense. The crew has to be tracking consumption and pressures every single day. A sudden jump stands right out on a graph.
But there's a more advanced test mentioned, the LDPT, low differential pressure test.
This is a really clever one. It's a health check for the secondary barrier that you can do while the ship is in normal operation.
Okay, walk me through it. How does that work?
Well, it starts with a pretest. They pressurize both the insulation space, the IS, and the interbarrier space, the IBS, to the same level, usually about 16 millibars.
So they puff both spaces up like balloons to the same pressure?
Exactly. And they watch them for an hour. If the pressure drops in both, they know they have an external leak somewhere, maybe a valve on deck. It's a sanity check.
And once they know the outside is tight,
they create a differential. They keep the IS at plus 16, but they drop the IBS down to plus 3. Now you have high pressure on one side and low pressure on the other.
And nature hates a vacuum or a pressure difference.
Exactly. If there are any holes in the barrier between them, gas will try to flow from high to low. And they measure how fast that happens. They call it the decay rate.
And I saw they have to normalize that rate, right? It's not just the raw number.
Yes, and that's critical. Gas behaves differently at different temperatures. If you didn't count for temperature, a test done in winter would give you totally different results from one in summer.
So the normalized decay rate, the NDR, lets them compare apples to apples over time.
Precisely. If that NDR starts creeping up, you know your barrier is degrading, and you can catch the problem months or even years before it becomes a critical failure.
It's just incredible. So much science just to watch gas move around.
It's the heartbeat of the vessel. You have to listen to it.
So to bring it all home, the crew found the leak in the LD1 compressor. They realized the carbon rings were probably too tight, and the plan was to adjust the pressure and just give the machine some run-in time.
A textbook resolution. They used logic and a deep understanding of the mechanics to turn a panic situation back into a manageable one.
It just goes to show these massive steel giants can be brought to their knees by a few millimeters of tolerance in a tiny carbon ring.
It's the butterfly effect of engineering, absolutely. A microscopic gap becomes a 22-hour runtime, which becomes a major safety risk. It's all connected.
And I just can't stop thinking about that run-in concept. We live in such a plug-and-play world. You buy a phone, you turn it on, it's perfect. If it's not, you send it back.
We've lost our patience for the break-in period. We expect instant perfection.
Exactly. But here you have this incredibly complex machine, and the solution is to just let it wear itself in. It feels almost organic, like a new pair of stiff leather boots. They hurt at first, but once they're worn in a bit, they fit perfectly.
It's a great reminder that engineering isn't always about rigid perfection. Sometimes it's about how materials settle and interact in the real world. Friction isn't always the enemy.
So, to our listener, the next time you feel like you're grinding against something new, a new job, a new skill, and it feels like there's too much friction, just remember the carbon ring. Maybe you're not broken. Maybe you just need a little more run-in time to create the perfect seal.
A comforting thought for machines and for people.
Thanks for diving deep with us today.
Always a pleasure.
We'll see you in the next one.